Hello everyone, welcome to our differential equation class. In this video we are going to introduce the Laplace transform method to solve differential equations. We are going to start with the general idea, how this method works, then the main definitions and properties of the Laplace transform, and then we are going to use all that to solve a differential equation with an initial condition. So that's the plan for today. Let's start with the general idea of the Laplace transform method, and to explain what this idea is and where does it come from, let's use an example. And the example is going to be a mass spring system that consists of a spring with spring constant k, an object attached to the spring with a mass m, and the spring oscillates in a medium with damping constant d. Let's suppose that the system is at rest, and at the time t equal t0, we hit the spring with a hammer in a way that we don't destroy the whole mass spring system. We want to be able to describe mathematically what happens in this case. And the difficult part here is to describe mathematically the force done by the hammer on the spring. This is a particular type of force that is called an impulsive force. An impulsive force has two main properties. The first one is that the force is zero at all times except at one single point in time when the force acts, and the intensity at that point in time is infinite. But is infinite in a particular way. We are not destroying the whole system. That means we are transferring to the mass spring system a finite amount of momentum and energy. What is the definition of the momentum? So let's review that. Recall that this system is described by Newton's equation of motion. The mass times the acceleration of the spring is equal all the forces acting on the spring, and in particular here we now include the impulsive force of the hammer. So suppose we integrate this equation in time. Then we need to integrate both sides of the equation, and suppose we integrate a little bit before the hammer strikes the spring, so t0 minus epsilon, and a little bit after, t0 plus epsilon, and we need to do the same here, t0 minus a little bit and t0 plus a little bit. This mass is constant, so it goes outside, and then we are integrating in time the acceleration. This is the velocity, and the velocity evaluated here minus the velocity evaluated there. So that is what we call the difference in velocity times mass. So we use this symbol delta to denote the difference in mass times velocity a little bit before and a little bit after the hammer strikes the spring. And on the other side, well, we have what we have is the integral of t0 minus a little bit t0 plus a little bit the integral of the force dt. Well, what we have over here is the momentum, is the definition of the momentum transfer to the system. So this is momentum. This is the momentum transferred to the system. That's the definition of momentum, the difference between mass time velocity before and after something happens, transfer. And Newton's equations say, well, it has to be the integral on those times of the forces acting on the system. And what we are saying here when we say the momentum transfer is finite is that this integral is finite. So these are the two properties that an impulsive force must have. Zero everywhere for all times except at one single point in time where the force is infinite, but is infinite in a very particular way, in a way that this integral is actually finite. So this is the system we want to be able to describe. So what is the equation then we need to solve? Well, the equation is Newton's equation of motion. Let's put the whole equation now. The whole equation is mass times acceleration, then the force of the friction force, then the force of the spring has to be equal all the external forces, and now the external force is the force done by the hammer. But this is an impulsive force. So we want to find a way to describe mathematically what happens here with an object here on the right hand side with these two properties. And one way to describe this situation mathematically is using the properties of the impulsive force, that the integral in time is finite. So the main idea then, the origin of the Laplace transform method, is to explain this type of situations by integrating the equation in time. So that is the main idea. The main idea is to deal with the right hand side of the equation, which is an impulsive force, by integrating in time the whole equation. Then this, right now, the right hand side is infinite at one point in time, and then zero everywhere else, which is a very weird right hand side. We can make it in a more reasonable right hand side if we integrate in time and we use this property of the impulsive force. So that's the whole idea of the Laplace transform method. Integrate the equation in time so we can be able to handle right hand sides, that they are impulsive forces. But then when we integrate in time, this is gonna be finite, but then we need to deal with this integral here. And what we are going to do over here? Well, the idea is to somehow, now that we are integrating in time, move this derivative somewhere else by integration by parts. So to be able to work on the left hand side, we are going to use integration by parts. So today, this video is going to be about what do we do on the left hand side, until we are pretty happy on how we work on the left hand side. Then, when we know how to work on the left hand side with the integration in time and the integration by parts, then we are going to focus back into the right hand side, and we are going to see how we can deal with the impulsive force. So to summarize, the Laplace transform method, the one possible explanation where this method comes from is to explain, to solve the problem with impulsive forces. Using the property of the impulsive force lead us to integrate in time the whole equation. That is going to fix the issues we have on the right hand side, but now we have new issues on the left hand side that we need to address. So the rest of the video is going to be what do we do when we have integration in time, and let's suppose we don't have the impulsive force. The impulsive force, we are going to deal with that later. Alright, so now we focus on the left hand side, and we want to use integration by parts there. So let's review the formula for integration by parts, which comes from the product rule for derivatives. The derivative of a product of two functions. Suppose you have f times g, and we compute the derivative. What do we know this is going to be equal to? It's going to be equal f prime g plus fg prime. The integration by parts formula comes from this equation. What we do now is we move one of the terms to the other side. So for example, we leave here f prime g, and then we put on the other side fg all prime minus fg prime. And now what happens if we integrate on both sides of that equation between a and b? Well, we are going to have the integral of f prime g dt, and on the other side is the integral of a total derivative, so it's going to be the original function evaluated at b minus the original function evaluated at a. This is the symbol for that. minus the integral from a to b of the other term, f g prime dt. And this is the formula for the integration by parts. This is integration by parts. This formula, we are going to use it a lot when we deal with the integrals in time of the left-hand side of the equation. To see how we are going to work here on the left-hand side, well, let's introduce a toy problem. Recall, right now we are forgetting about the impulsive forces. The impulsive forces give us the main tool to solve this problem, which is integrate in time. But since we are going to integrate in time, now we are going to need to deal with the left-hand side. So let's forget about the impulsive forces and let's see what we can do with the left-hand side when we integrate in time. And let's try to use this integration by parts formula for that. So again, let's focus on the left-hand side and let's simplify the left-hand side with just one derivative. We are going to move this term pretty soon to the other side. No impulsive forces. Suppose we want to solve an initial value problem, very simple initial value problem with some initial condition. And the way we want to solve it is somehow integrate in time the whole equation. These are the main idea now, because integrating by time, one last time, integrating on time is going to help us deal with impulsive forces later on when we add it to the system. So, solution. How do we solve this problem when the main idea is integrating time, the whole equation? Okay, let's move the term negative 3y to this side. So recall, we want also to use the formula integration by parts, and for that we need two functions. So this derivative goes here by doing integration by parts. So we need a second function here. So let's multiply the whole equation by a function of t. And on the left-hand side we still have 0. And now that we do this multiplication, now we can integrate in time. So we are going to have, let's distribute also. So we are going to have mu times y prime. Then we have minus 3 mu y, all that equal 0. And now we are going to integrate this whole thing in time. We are going to integrate in time. But not an indefinite integral. We want a definite integral because this is an initial value problem and we are interested in the solution from 0 to positive values. So because of that, we are going to use here integration from 0. We are going to start at 0. And then what is the end limit of integration? Well, we want any possible time, so we are going to integrate up to infinity. Now, since this is a definite integral, on the right-hand side, this is still 0. And now, we are going to split the integral on the left-hand side. So we are going to have the integral from 0 to infinity of mu y prime dt. And then minus the 3, we can take it outside of the integral, mu y dt from 0 to infinity equals 0. And here is where we are going to use the integration by parts formula, and we are going to move this integral to the other side. So here we are going to use the integration by parts. But the calculation is going to be simple or complicated depending on what is this function mu. If we put a function mu that is super complicated to compute the derivative, we are going to end up in big troubles. So now we need to choose a function mu, and we are going to choose it so that it's very easy to compute the derivative. So it's up to us to choose this function mu. So we are going to choose it to be just an exponential because derivatives are super easy here. But also we have integrals from 0 to infinity. This integral may diverge if we choose an increasing exponential. The exponential is going to make everything worse. So let's choose an exponential that helps this integral to converge, and that means an exponential of this form, negative st. S is a constant, but now S is a positive constant, positive constant. So let's write it well, positive. So we are talking about a function of this form, and that is going to help all these integrals to converge. So the idea then is, if we have to integrate the equation to solve it, and we want to use integration by parts, maybe then a good idea is to do the following. You have your original equation, y prime. Let's write it like this, minus 3y equals 0. So then maybe it's a good idea to multiply the whole equation by exponential negative st, s positive. Let's multiply here also by negative, so exponential negative st. Let's do that. Multiply 0 by exponential is still 0, and then integrate in time from 0 to infinity, because this is where we want to find the solution. We have an initial value problem. And then now what we do is, finally, we use integration by parts to move this derivative to the other side by here, integration by parts. So this is the integration by parts. This is in a nutshell how we are going to use integration and integration by parts to try to solve a differential equation. And recall, the whole idea here of doing this integration and the multiplication and everything is because later on we are going to change that by an impulsive force, and we need this integral in time to work with finite quantities. But this is the main idea of the Laplace transform method to solve differential equations, to do all these calculations to solve the differential equation. We are going to continue this calculation at the end of the video, but right now we need to introduce some definitions and properties of this whole calculation here. So before we do that, let's go a little bit on who worked on these ideas first, and of course was Leonhard Euler in 1737, which introduced these ideas to deal with second-order differential equation with constant coefficients, which are the equation we are going to work in these videos. Then Joseph Lagrange proved more properties of use this type of equations on other equations, on the wave equation, to describe the propagation of sound. Then Laplace came back to these ideas and proved many properties of this type of calculations, and he did a lot of work in 1782 and 1810. That's why these ideas are named after him. But it was Gustav Deutsch in 1937, pretty recently, that uncovered again all these ideas and used it a lot in solving problems for springs and electric circuits in mechanical engineering and electrical engineering. And he popularized these methods a lot and introduced the notation we are going to use, that is used nowadays. So this is a little history of these ideas, and now we are going to go into the details, the definition and the properties of this type of operations. So this whole discussion leads us to the following definitions. The Laplace transform of a function f of t that is defined on the domain 0 infinity is given by this expression, where what we have on the right hand side is our function f of t multiplied by an exponential negative st, and then integrated this product in between 0 and infinity. And when we do all these calculations, what we are going to end up is with a number that actually depends on the value of s we put here. So actually this is a function of s. And this function of s may be defined or not for depending on the values of s. So we are going to say that this function of s is going to be defined on some domain where this integral converges. So that is now the Laplace transform of a function. And notice that the Laplace transform is actually a function, because it's an operation on a function that gives us another function. And when that happens, we call that a transformation or an operator. So actually, what we have here is a function, because the Laplace transform of something is grab that something, whatever that is, multiply by the exponential negative st, and then integrate that something in dt from 0 to infinity. So if you want to put there a function, any function f of t, then you put your function here and do the calculation indicated. And then you're going to obtain a new function. So that's why we have this other notation that this is actually a function of s, wherever this integral converges. So that's the Laplace transform. Notice the Laplace transform contains, of course, an improper integral. An improper integral means that we have a limit that is infinity. And what that means, let's recall that the definition of an integral to infinity is we integrate until a finite value. We do this integral first. We have an expression here that depends on this n, and to that expression we take the limit n goes to infinity. So that's how we define improper integrals. So now let's see how this definition works in an example. And the example here is, let's compute the Laplace transform of an exponential at. A is any real number, but in our calculation we are gonna set a particular value of a. Let's set oh, this is not right. Okay, let's set finally a equal 3, for example. So let's do the calculation with 3, and then we are going to see that it's very easy to generalize to any other value. So solution, how we compute the Laplace transform of exponential 3t. What do we need to do? Well, what we said we have to do, we grab the exponential 3t, we multiply that by the exponential negative st, and then we integrate the whole thing from 0 to infinity in time, in t. And when we say integral to infinity, what we mean is the limit n going to infinity of the integral up to a finite value, 0 big N. And here we can use the property of the exponential and start rewriting this as the exponential of 3 minus s times t dt. So it's just one single exponential. And recall, when we have one exponential, what is the integral of that? If we have the integral of exponential alpha t dt, this is of course 1 over alpha, the same exponential. So let's recall that, because we are gonna need it. But we have before we use that, so notice, if we want to use this formula, we need to divide by this coefficient, but this coefficient could be 0 if we for some reason choose s equal 3. If we choose s equal 3, this coefficient is 0 and we cannot do this integral. So we need to consider the case s equal 3 first. Recall, s here is arbitrary. S is any constant. So let's say here S is any constant. Could be 3. So if it's 3, what happens? Well, if S happens to be 3, then what is the Laplace transform in that case? When we put S equal 3, exponential 3t is going to be the integral, the limit, n goes to infinity, of the integral of 1 from 0 to n of 1 dt, isn't it? Because this is 0 and the whole thing is 1. And that is going to be the limit n goes to infinity of n. And that is infinity. So the integral diverges here. So if S is equal 3, then the Laplace transform of exponential 3t diverges. So diverges. Recall what we said in the definition. We call that integral the Laplace transform whenever for the values of S where this integral converges. Well, in our first example, we have a value that is not in the domain of the Laplace transform because for S equal 3, that integral diverges. Okay, so let's assume now that let S is different from 3. Okay, now it's much simpler because if S is different from 3, then we can actually use this formula to compute the integral because this quantity here is different from 0. So now we have the Laplace transform of the exponential 3t, and that is going to be now the limit n goes to infinity, and now we can divide by 1 over 3 minus s, and then we have the same exponential 3 minus s multiplied by t evaluated in 0 and n. So that is the integral, and now we can rewrite this integral as the limit n goes to infinity 1 over 3 minus s. Okay, we evaluate at n and we have exponential 3 minus s times n minus at 0, which is 1. So this is what we get, and actually we can this quantity doesn't depend on n, so we can put the limit here and move this thing outside. And what do we do now? Well, the limit is actually only here, so and there are two possible results. So as we are going to see pretty soon, there are two possible results, one or the other, depending on the value of this constant here. Suppose this constant s minus 3 is positive, so, or 3 minus s, sorry. Suppose this is positive. Well, if this is positive and then we multiply by n and we take the limit n goes to infinity, we are talking about an exponential that is increasing in n because the coefficient 3 minus s is positive. So this is a function that increases with n. So the limit here is infinity. But the other possibility is that s, so 3 minus s is actually negative. Oh, then we have an exponential as function of n with a negative exponent, so it's something like this. It goes to 0, the limit. In that case, it goes to 0. So notice that the first case is s is this is equivalent to, if we move s to the other side, to s be smaller than 3, and here to s to here to s to be bigger than 3. So only in this case we have a convergent integral, on the other case is divergent. So what we can say is if s is smaller than 3, then the Laplace transform of the exponential 3t diverges, which is the same that happened when s is equal 3. And if s is bigger than 3, then what do we have? Then what we have is a very nice formula for the integral, because the Laplace transform of exponential 3t in this case is going to be 1 over 3 minus s. We take the limit, and then we are going to get a 0 there. So we are going to get 0 minus 1, and that implies that we have a final formula for the Laplace transform of the exponential 3t, which is 1 over s minus 3, and this is only true for s bigger than 3. And this is our first Laplace transform. Notice we need to put the domain. The calculation, the integration we have done can only be done for s bigger than 3, and in that case we get that result. Notice that this function is defined for s different from 3. Is defined for every s. This is also defined for s smaller than 3. The result is defined, but the calculation we needed to actually compute this result is not defined for s smaller than 3. That's why the domain of the Laplace transform is s bigger than 3. We can repeat this calculation for now changing back 3 into a, and you put a here all over, and you're going to see that it's very easy to see that the result of exponential at is actually s minus a for s bigger than a. And this is the Laplace transform of an exponential. The idea now is to compute Laplace transforms of several functions and create a little table, a table of Laplace transforms that looks more or less like this. So what we have done is, where are we? We are here. So we have done this Laplace transform. I don't like it. So we have done this Laplace transform. A little bit better. And notice that if we, for example, consider the case a equals 0, then the exponential is 1, and actually we have proven this result also. So this Laplace transform, the function 1, is a particular case of the exponential when a is 0. So we have proven these two entries in the table, and the idea now is to do homework and construct the rest of this table. So for example, the Laplace transform of t to the power n is going to be given by this function. The Laplace transform of a sine function is going to be given by that expression, and so on. Construct this table by doing the same calculation we have done for the exponential. Now let's go briefly on the main properties of the Laplace transform. The first property is that it's a linear operation. The Laplace transform of if a and b are constant, the Laplace transform of a linear combination of two functions is the linear combination of the Laplace transforms. This is very simple to prove because we are talking about integration and multiplication. So the Laplace transform the Laplace transform of a constant times a function plus another constant times another function. This is the integral from 0 to infinity. Recall exponential negative st multiplies the whole thing a f of t plus b g of t dt. So now we can multiply the exponential on both terms, and because a and b are constants, we can move them outside. So a integral from 0 to infinity of exponential negative st f of t dt, and then plus b, the integral from 0 to infinity of exponential negative st, now multiplied by only by g of t dt, and this is just nothing more than a, the Laplace transform of f, plus b, the Laplace transform of g. So there it is. This is the linearity property. Very simple to prove. But there are a few remarks, because it's very easy to get confused and to say things that they are not true. What is true is that a particular case is when b is 0. So when b is 0, this is not there, and then so this is not there, this is not there, and then when we have a constant, the constant goes outside. Okay, this is what we say here. If we have a constant times a function, the constant can be written outside the Laplace transform, or if we have a constant outside, we can put it inside. This goes both ways. This is a particular case of the linearity property. But if c is not a constant, then we cannot take it outside, because that works only with constants. So it's not true that if we have a product of two functions, one can go outside. And also it's not true that if we have a product of two functions and we compute the Laplace transform, this is not the product of the Laplace transforms. For linear combinations, it is with constants. The Laplace transform of the linear combination is the linear combination of the Laplace transforms, but the Laplace transform of products is not the product of the Laplace transforms. Okay, this is the property of linearity. Another property, the most important property actually that we want in the Laplace transform, is the property of the derivatives into multiplications, which is the following. Suppose we have a function f of t that is differentiable and is bounded by an exponential. We need this property on the function f, so the Laplace transforms are well defined. There are many functions where this is not true. For example, fails for one example that the function is not bounded by an exponential is when we have f of t is an exponential of, let's say, t squared. Well, that property is not going to be true then. So there are many functions we can think of where we cannot compute the Laplace transform, but there are many others that we can't. All these functions that they are bounded by an exponential. For those functions, this equation holds. And this equation says that the Laplace transform of a derivative of a function is equal to the Laplace transform of the function without the derivative multiplied by an extra factor s, and then there is some extra term here. So that means that the derivative that we have here is changed into a multiplication. And to do that, we need integration by parts. So what is the idea of the proof? We are going to do it pretty quick, but suppose we want to compute the Laplace transform of a derivative of a function. Okay, so we know what that is. That is the integral from 0 to infinity of exponential negative st, and then the derivative of the function dt. But of course, what we are going to do is we are going to integrate by parts. That's the whole idea behind this method of solving differential equation by integration. we do integration by parts, and what we get here is the exponential negative st, the function of t evaluated at 0 and infinity, minus the integral of from 0 to infinity, and now here we have the exponential negative st derivative f of t dt. And you see where the multiplication by s is gonna come from. Here we have the limit n goes to infinity. Recall what we mean by this infinity here, where we take the limit of exponential negative Sn Fn, and then minus at 0. At 0 we have f at 0 only. And then here we have a positive s that we can take it outside of the integral because the integral is on time. Well, let's put it inside and then emphasize that we can take it outside. And here let's keep it like that. Minus s exponential negative st f of t dt. Of course, now we are gonna move that outside. Oh, I forgot the limits, 0, infinity. The negative signs are gonna cancel, and now this limit is gonna be 0. Why this is 0? This is 0 because of this hypothesis here makes that limit 0. And then what we are going to have is something of the form 0 minus f at 0, and then plus s, and what we have here is the integral from 0 to infinity exponential negative st f of t dt, and this is of course the Laplace transform. The Laplace transform of f. So we end up with the formula that the Laplace transform of the derivative of a function is actually equal s times the Laplace transform of the function without the derivative, and then there is an extra term that comes from the integration by parts. And this is how we prove this result, which is a very important result because it changes, the Laplace transform changes derivatives into multiplications. 2 remarks and we are done with this result. Of course, this part of the proof where we can cancel this term is not true when we have functions that they don't satisfy this hypothesis. And the other remark is, once we have this result proven, this formula, we can use this same formula to prove what is the Laplace transform of higher derivatives. Because what you do here is you write this Laplace transform of the second derivative is just the Laplace transform of a first derivative prime. So now use this formula, with this function here, and then use it again. Use this formula twice, and then you're gonna get this formula here. All right. These are the main properties of the Laplace transform, and now we are ready to use all that to solve a differential equation. And recall, we were working on this problem. We wanted to solve this differential equation using the Laplace transform method. This is an initial value problem. Recall, we know what the solution of this problem is, isn't it? This problem, the solution is, of course, y of t equal to exponential 3t. We know that. But this is a toy problem, an example to solve it with the Laplace transform method. So, solution. Recall, we have our equation, we put it on, the whole idea was to write the equation as y prime minus 3y equals 0. Then what we wanted to do is we wanted to multiply the whole equation, by exponential negative st, and also on the other side exponential negative st, and then we integrate in time between 0 and infinity, and then we use integration by parts to move that derivative to the other side. That was the whole idea. And this is exactly what we are going to do, but we are going to use it now. We are going to do it using a much nicer notation, because all that we have done here now is called the Laplace transform. So we have the equation y prime minus 3y equals 0, and what we do now is we compute the Laplace transform of that. Which is what we did here. But actually on this side is 0, and on this side we use linearity, and this is what we get: Laplace transform of y prime minus 3 Laplace transform of y. This is equal 0. Okay, now we use the property on the derivative, which is the integration by parts. And the integration by parts says that this is going to be s Laplace transform of y minus y at 0. Then we have here minus 3 Laplace transform of y is equal 0. Now the initial condition says that this actually is given. That's why we are integrating from 0, because we can use the initial condition and say that this is equal to. So now we can pull common factor Laplace transform of y, and we have s minus 3 Laplace transform of y minus 2 is equal 0. Now you see we have an algebraic equation instead of a differential equation. This is an algebraic equation, because derivatives were changed into multiplication by integration by parts. This algebraic equation is super easy to solve. We move the 2 to the other side, and we divide by s minus 3, and this is how we solve for L of y. So the Laplace transform of our solution to the differential equation is 2 over s minus 3. And now we need to find a y of t such that this happens. But what did we prove before? Before we showed that the Laplace transform of any exponential at is 1 over s minus a. So if we say a equal 3, like when we did the calculation, what happens? Well, what happens is that 1 over s minus 3 is actually the Laplace transform of the exponential 3t. So what we can do is we can say that the Laplace transform of the function we are looking for is actually 2, of course, over s minus 3, and this is the same as 2 the Laplace transform of the exponential 3t, and because of linearity this is the same as the Laplace transform of 2 exponential 3t. So you see the two Laplace transforms are the same. So one solution to this equation, and later on one can prove the only solution, is that y of t is 2 exponential 3t. So this is how we can use integration by this is not good. This is how we can use integration by parts to solve differential equations. We change derivatives into multiplications. We change derivatives into multiplication. We get an algebraic equation for the Laplace transform of the solution. Algebraic equations are super simple to solve. We solve the algebraic equation, and now the whole problem is to find a function such that the Laplace transform is given by this expression, but with our work on constructing the Laplace transform table, we have one entry in the table that satisfies exactly that, so we were lucky with this equation. Then we can change that into a Laplace transform, and therefore the solution has to be that function. So this is the essence of the Laplace transform method, where it comes from, how to use it to solve the differential equation that has no forces, and the whole idea is going to work later on when we have impulsive forces on the right hand side. So this is all for this video. This is a good place to stop. See you guys in the next video.